Grounding a 1200 amp 3-phase 120/208 volt service with 6 meters requires careful attention to detail and adherence to electrical codes. Firstly, gathering the necessary materials is essential. This includes a ground rod that is 8 feet minimum in length, a ground clamp suitable for connecting to the ground rod, copper ground wire with a size of 6 American wire gauge, a grounding electrode conductor with a minimum size of 500 kcmil, and a copper ground bus bar rated for 1200 amps. Secondly, installing the ground rod correctly is crucial. Drive the 8-foot ground rod into the earth, ensuring it is at least 10 feet away from any building or structure. Then, securely tighten a ground clamp around the top of the ground rod. Thirdly, the grounding electrode conductor must be properly connected. Connect the 500 kcmil grounding electrode conductor to the ground clamp that is mounted in the ground rod. Run this conductor to the tap box, maintaining its integrity along the way. Fourthly, bonding the tap box to ground is a critical step. Connect the grounding electrode conductor to the ground bar, which should be installed inside the tap box. Further, connect the tap box to the ground bar using a 6 American wire gauge copper ground wire. Fifthly, each meter can needs to be bonded to the ground bar. Run 6 American wire gauge copper ground wires from the ground bar to the terminal block of each meter can, ensuring each connection is secure and tight. Sixthly, grounding the neutral conductor is essential for safety and proper system operation. Connect the neutral conductor to the ground bar using an appropriately sized ground wire with a minimum size of 500 kcmil. Seventhly, the grounding electrode conductor must be bonded to the neutral conductor. At the point where the grounding electrode conductor enters the tap box, bond it securely to the neutral conductor using a ground clamp or a suitable connector designed for this purpose. Some additional notes to consider include the fact that all ground connections must be made using materials and methods that are approved for electrical use. Refer to local electrical codes and regulations for specific requirements that may apply in your area. It is highly recommended to use a qualified electrician to perform these tasks, as they have the knowledge and experience to ensure the grounding system is installed correctly and safely. Ensure that the ground path is continuous and exhibits low resistance, which is critical for effective fault current dissipation. After completing the grounding installation, it is essential to test the ground system using an ohmmeter to verify proper connectivity and low resistance. A high resistance reading indicates a problem that needs to be addressed immediately. The grounding electrode conductor serves as the primary path for fault current to return to the source, allowing overcurrent protection devices like circuit breakers to trip and clear the fault. The size of the grounding electrode conductor is determined by the size of the service entrance conductors as specified in the National Electrical Code, NEC Table 250.66. For a 1200 amp service, with multiple sets of 500 kcmil conductors, a minimum 500 kcmil copper grounding electrode conductor is typically required. The ground rod itself provides a supplemental grounding path to earth, helping to stabilize voltage and provide a path for static discharge. While a single ground rod is often sufficient, installing multiple ground rods spaced at least 6 feet apart can further reduce ground resistance. The tap box serves as a central point for connecting the service entrance conductors to the individual meter cans. Bonding the tap box to the grounding system ensures that it is at the same electrical potential as ground, preventing voltage differences that could create a shock hazard. The meter cans house the individual meters that measure the electrical consumption of each unit or tenant. Bonding each meter can to the ground bar ensures that they are also at ground potential, enhancing safety. The neutral conductor is the return path for current in a 120/208 volt system. Grounding the neutral conductor at the service entrance establishes a reference point and helps to stabilize voltage. The connection between the grounding electrode conductor and the neutral conductor is known as the main bonding jumper. This jumper provides a low impedance path for fault current to return to the source. The size of the main bonding jumper is determined by the size of the service entrance conductors as specified in NEC Table 250.102 cone. The 6 American wire gauge copper ground wires used to bond the tapworks and meter cans provide a supplementary grounding path. These wires help to ensure that all metallic enclosures are at ground potential, reducing the risk of electric shock. When making ground connections, it is essential to use appropriate connectors and methods. Compression connectors, also known as crimp connectors, provide a reliable and secure connection that will not loosen over time. Exothermic welding, also known as a cat weld, creates a permanent metallurgical bond that is highly resistant to corrosion and vibration. Mechanical connectors, such as set screw connectors, are also acceptable, but they must be properly tightened and inspected periodically to ensure they remain secure. All ground connections should be made in a manner that is accessible for inspection and testing. Avoid burying ground connections or concealing them behind walls or other obstructions. When running grounding conductors, protect them from physical damage. Use conduit or other protective measures to prevent the conductors from being cut, abraded, or otherwise damaged. Ensure that all grounding conductors are continuous and without splices. Splices in grounding conductors can create high-resistance connections that compromise the effectiveness of the grounding system. When installing ground rods, drive them deep enough into the earth to reach moist soil. The depth required will vary depending on the soil conditions in your area. In general, the top of the ground rod should be at least 8 feet below grade. When connecting to a ground rod, use a ground clamp that is specifically designed for that purpose. Avoid using generic clamps or connectors that may not provide a reliable connection. When bonding metallic enclosures, such as the tapworks and meter cans, use bonding bushings or bonding jumpers to ensure a low impedance connection. Bonding bushings are installed on conduit entering the enclosure and provide a connection point for the grounding conductor. Bonding jumpers are used to connect separate pieces of metallic conduit or to bond the enclosure to the grounding system. When grounding electrical equipment, follow the manufacturer's instructions and recommendations. The manufacturer may specify specific grounding requirements or methods that must be followed. When working on electrical systems, always de-energize the circuit before making any connections. Use a voltage tester to verify that the circuit is de-energized before proceeding. Wear appropriate personal protective equipment, such as gloves and safety glasses, to protect yourself from electrical hazards. If you are not comfortable working on electrical systems, hire a qualified electrician to do the work for you. Electricity is dangerous, and it is important to take all necessary precautions to protect yourself and others. A properly grounded electrical system is essential for safety and reliability. By following these guidelines and adhering to electrical codes, you can ensure that your 1200 amp 3-phase 120/208 volt service with 6 meters is properly grounded and protected. Remember to consult with a qualified electrician if you have any questions or concerns. Grounding is a critical aspect of electrical safety. Firstly, it provides a low impedance path for fault currents, which helps to quickly trip circuit breakers or fuses, minimizing the risk of electrical shock and fire. Secondly, it helps to stabilize voltage levels, reducing the likelihood of voltage fluctuations that can damage sensitive electronic equipment. Thirdly, it provides a path for static electricity to dissipate, preventing static buildup that can damage electronic components or create a shock hazard. A properly grounded system also helps to reduce electromagnetic interference, (EMI), which can disrupt the operation of electronic equipment. Grounding is not just about connecting wires to the earth. It is about creating a comprehensive system that ensures all metallic enclosures and conductive parts are at the same electrical potential. This equipotential bonding minimizes the risk of voltage differences that can create a shock hazard. The grounding electrode system consists of the grounding electrode, which is typically a ground rod or a metallic water pipe, and the grounding electrode conductor, which connects the grounding electrode to the service equipment. The grounding electrode should be installed as close as practical to the service equipment and should be accessible for inspection and testing. The grounding electrode conductor should be sized according to the size of the service entrance conductors. The equipment grounding system consists of the equipment grounding conductors, which connect the metallic enclosures of electrical equipment to the grounding system. The equipment grounding conductors should be sized according to the size of the circuit conductors. The neutral conductor is grounded at the service entrance to establish a reference point and to provide a path for fault current to return to the source. The connection between the neutral conductor and the grounding system is called the main bonding jumper. The main bonding jumper should be sized according to the size of the service entrance conductors. In addition to the main bonding jumper, there may be additional bonding jumpers required to bond other metallic parts of the electrical system, such as metallic water pipes and gas pipes. These additional bonding jumpers help to ensure that all metallic parts are at the same electrical potential. Ground fault circuit interrupters, GFCIs, are devices that are designed to protect people from electrical shock. GFCIs monitor the current flowing in the circuit and trip the circuit if there is a ground fault. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, AFCIs, are devices that are designed to protect against fires caused by arcing faults. AFCIs monitor the current flowing in the circuit and trip the circuit if there is an arcing fault. AFCIs are required in many locations, such as bedrooms and living rooms. Surge protective devices, SPDs, are devices that are designed to protect electrical equipment from voltage surges. SPD divert the surge current to ground, protecting the equipment from damage. SPD are recommended for all electrical systems, especially those that serve sensitive electronic equipment. Regular inspection and testing of the grounding system is essential to ensure that it is functioning properly. The grounding system should be inspected visually for any signs of damage or corrosion. The grounding electrode resistance should be tested periodically to ensure that it is within acceptable limits. If the grounding electrode resistance is too high, it may be necessary to install additional ground rods or to improve the soil conductivity. Grounding is a complex topic, and it is important to consult with a qualified electrician if you have any questions or concerns. A qualified electrician can help you to design and install a grounding system that meets your specific needs and complies with all applicable codes and standards. Proper grounding is essential for the safety and reliability of any electrical system. By following these guidelines and consulting with a qualified electrician, you can ensure that your electrical system is properly grounded and protected. The NEC, specifically Articles 250.24 and 250.28, covers the requirements for grounding and bonding in electrical systems. These articles provide detailed information on the size and installation of grounding conductors, bonding jumpers, and other grounding components. It's crucial to adhere to these requirements to ensure a safe and effective grounding system. Also, NEC Section 250.50 discusses grounding electrode systems and the requirements for different types of grounding electrodes, such as ground rods, metal water pipes, and concrete encased electrodes. Understanding these requirements is essential for selecting and installing the appropriate grounding electrode for your specific application. The NEC also addresses the bonding of metal enclosures and equipment to ensure a lower impedance path for fault currents. This bonding is critical for minimizing the risk of electric shock and fire. NEC Section 250.92 covers the bonding of metal enclosures containing service entrance conductors. Additionally, NEC Section 250.96 addresses the bonding of other metal enclosures and equipment. These sections outline the requirements for bonding conductors and methods. Furthermore, the NEC provides specific requirements for grounding and bonding in healthcare facilities, industrial locations, and other specialized applications. These requirements are designed to address the unique electrical safety challenges in these environments. It's essential to consult the relevant NEC articles for your specific application to ensure compliance. When designing and installing a grounding system, it's important to consider the soil conditions in your area. Soil resistivity can significantly impact the effectiveness of the grounding electrode. High soil resistivity can require the installation of additional ground rods or the use of ground-enhancing materials to achieve an acceptable grounding resistance. Local electrical codes may also have additional requirements for grounding and bonding. It's important to consult with your local electrical inspector to ensure that your grounding system complies with all applicable codes and regulations. Remember that grounding is not a one-size-fits-all solution. Specific requirements for grounding will vary depending on the size and type of electrical system, the soil conditions, and the applicable codes and regulations. A qualified electrician can assess your specific needs and design a grounding system that meets all requirements. It's also important to note that grounding is not the same as bonding. Grounding provides a path for fault currents to return to the source, while bonding ensures that all metal enclosures and conductive parts are at the same electrical potential. Both grounding and bonding are essential for electrical safety. When installing a grounding system, it's important to use high-quality materials and components. This includes grounding conductors, bonding jumpers, connectors, and ground rods. Using substandard materials can compromise the effectiveness of the grounding system and increase the risk of electrical shock and fire. Also, make sure that all connections are properly tightened and secured. Loose connections can create high resistance points that can impede the flow of fault current. It's also important to protect grounding conductors from physical damage. Exposed grounding conductors can be easily damaged by equipment or vehicles. To protect grounding conductors, use conduit or other protective measures. Finally, remember that grounding is a critical aspect of electrical safety. Never attempt to work on a grounding system unless you are qualified and experienced. If you have any questions or concerns, consult with a qualified electrician. Also consider that the 500 kc minimum size mentioned for the grounding electrode conductor might need to be larger depending on the specific details of the service entrance conductors and the applicable NEC tables. Always refer to the latest edition of the NEC and consult with a qualified electrician to determine the correct size for your specific installation. The intent of bonding is to create a low impedance path between all metal parts that are likely to become energized. This helps to ensure that fault currents can quickly flow back to the source, tripping the overcurrent protection device and minimizing the risk of electric shock. When bonding metal enclosures, it's important to use listed bonding fittings and connectors. These fittings are designed to provide a reliable and low impedance connection. Avoid using makeshift bonding methods such as wrapping wire around a pipe, as these methods are not reliable and can create a safety hazard. The ground rod should be driven into the earth until at least 8 feet of its length is in contact with the soil. The top of the ground rod should be flush with or below grade to protect it from physical damage. If bedrock or other obstructions prevent you from driving the ground rod to its full length, you can bury it horizontally in a trench at least 30 inches deep. When installing multiple ground rods, they should be spaced at least 6 feet apart. This spacing helps to prevent the ground rods from interfering with each other and reduces the overall grounding resistance. The grounding electrode conductor should be run in a straight line without any sharp bends. Sharp bends can increase the impedance of the conductor and reduce its effectiveness. The grounding electrode conductor should be securely fastened to the building structure to prevent it from being damaged or dislodged. When connecting the grounding electrode conductor to the ground rod, use a listed ground clamp that is compatible with the size and material of the conductor and the ground rod. The ground clamp should be tightened securely to ensure a low resistance connection. After the grounding system is installed, it should be tested to verify that it meets the requirements of the NEC and other applicable codes. The grounding resistance can be measured using a ground resistance tester. If the grounding resistance is too high, it may be necessary to install additional ground rods or to improve the soil conductivity. A qualified electrician can perform this testing and provide recommendations for improving the grounding system. In addition to the grounding electrode system and the equipment grounding system, there is also the separately derived system grounding. A separately derived system is an electrical system that is powered by a generator, transformer, or other source that is not directly connected to the utility grid. Separately derived systems must be grounded in accordance with the requirements of the NEC. The grounding requirements for separately derived systems are similar to those for service entrance systems, but there are some differences. For example, the grounding electrode conductor for a separately derived system must be connected to a grounding electrode that is located at the source of the separately derived system. The neutral conductor of a separately derived system must be bonded to the grounding electrode conductor at the source of the separately derived system. Grounding and bonding are essential for the safety and reliability of electrical systems. By following the requirements of the NEC and other applicable codes, you can help to ensure that your electrical system is properly grounded and bonded and that it is safe for yourself, your family, and your employees. Always consult with a qualified electrician if you have any questions or concerns about grounding and bonding.